Oops. Okay, I have no idea if you've got all that. You got that written down for me, babbling on here? You guys are pretty good. So primarily, first, we've got to talk about the orbital filling order. How are we going to load the electrons into our atom? We need a handful of rules that we use to fill the orbitals with electrons. So essentially, in the logic, we've defined our orbitals. Now we're going to state the rules in which we fill the orbitals with. So we're going to use these rules to load up our orbitals. Again, our analogy of the dorm room, we're going to use rules like this to kind of fill the dorm room as students come in. And then next we're going to talk about that energy, that energy filling order. Great names on this stuff comes from the physicists / chemists, whether they were physicists or chemists, likely physicists, working on this in the 30s and 40s. That essentially came up with these ideas, these rules. Some of them might have been determined experimentally, but most of them would have been determined theoretically based on the mathematics that came out of this quantum mechanics, this complex mathematics. And when we start adding electrons to our orbitals, we use these rules in this order to guide us. Now, each of these rules can be understood from our point of view of just learning some quantum mechanics. It's not that these are just totally, off-the-wall things coming from some kind of crazy science. The first one, called the Aufbau principle, and I sometimes on multiple choices make you to state which rule is which. I always say the Aufbau principle starts with an A, so that's my first rule. You know what I mean? I'm using little mental tricks to help me remember which one goes with which. The Aufbau principle states that when you start adding electrons, you fill them in the order of increasing energy, which means you start with the lowest orbital energy, you fill it up, and then when it's full, you move to the next higher orbital energy, and you fill it up. And then you move to the next higher orbital energy, and you fill it up. So you fill them in the order of increasing energy. Start at the bottom, where the lowest energy is, and you fill it up, and you keep filling up as you move up. If we really think about this, this is any regular law of physics. If you're filling anything, like a hole or a bowl, you always fill the lowest energy position first. If you're pouring, say, M&Ms into a bowl, where's the lowest energy position in the bowl? Yeah, at the bottom. So when you pour M&Ms into a bowl, you always fill the bottom of the bowl first. Makes sense, doesn't it? You can't fill the top of the bowl first and then fill the bottom of the bowl after that. Think about it. An atom is really an analogy for a bowl that holds electrons. And instead of gravity pulling the M&Ms to the bottom of the bowl, we have an electrostatic force, the opposite charge of the nucleus and the electron, that pulls the electron to the bottom of the atom bowl first. So the Aufbau principle just makes sense. You fill the lowest part of the energy bowl in the atom, which is the lowest energy orbital, first. And when it's full, you move to the next spot that's available. So what does the Aufbau principle say? Always fill a bowl from the bottom to the top when you're filling a bowl. Makes good sense, doesn't it? All right. So we start at the bottom and we move up. Hund's rule. Orbitals of a particular sublevel must be half filled with one electron before pairing them. If I get to a p subshell and there's 3 of those orbitals, I won't put 2 electrons in each p orbital. I'll fill them individually first until they've got 1 electron in each, and then the next electron will start to pair them up. So in the dorm room analogy, if you've got 3 rooms and they each have 2 beds in them, and 3 students come along, you'd probably want your own room. You can study better. You don't have to worry about your roommate snoring. So you fill the rooms with 1 first, and then when you're forced to, because more students come along, you then pair them up. All right? Now, in terms of a physical reality and why that happens, all electrons are negative. They're going to repel each other away to the point where they'd rather be apart from each other than paired up. So if there's only, say, 3 in the p orbitals, they're going to spread each other out. Once you've got that half filled, the Pauli exclusion principle comes in. Each orbital can hold a maximum of 2 electrons, which must be spinning in the opposite direction. And that essentially means once you've half filled the p orbitals, for example, if you have more electrons come in, you then pair them up until they have 2 orbitals or 2 electrons in each. Okay? So they'd rather be apart if they could be, but if they have to, you can put 2 electrons in each orbital, but they must be spinning the opposite way. The reason they can fit into 1 orbital with the opposite spin has to do with magnetic fields. And if you don't understand what I'm going to say next, it's not a problem, but if you do, that's great. You learned in grade 11 physics that when you have charges going around like a coil, you use something called Lenz's law with the, did you use the left-hand rule or the right-hand rule? Left-hand rule, that means you guys were talking about negative charges moving, right? Right. You use the left-hand rule to determine which end is north. A spinning electron is a rotating charge, just like a coil with charge going around it. You can use the left-hand rule to determine the actual north pole of the magnetic field caused by that rotating electron. Rotating electrons produce magnetism. You take one that's spinning up and one that's spinning down. Sorry, I've got to use my other left hand here, if you can get the idea. I know I'm doing it wrong, but you end up with 2 electrons that have opposite poles next to each other, and they'll literally be slightly attracted to each other by these opposite poles. So they'll kind of stick together like little magnets. Even though they're repelled from each other, because they're both negative, there's a weak magnetic field that will allow them to sit in that same orbital together. If you did not understand any of those words that I just said a moment ago, don't worry about it. It's not a big deal. But that's why they pair up, because they do have that opposite spin, which produces opposite magnetic fields. Okay, so these are the rules that we use to fill. I'll address them when we start filling them. Now let's talk about, we got to go back to the first rule here. What is that order in which we fill the orbitals? What is the order in which we put them together? And it's not that nice. So you can write what's in the box, but don't worry about the picture. I'm going to be addressing the picture in a moment. So there are two things that come into play here. One is stated in the first bullet, and this you haven't heard yet, and that's because, well, I didn't mention it. That's the only reason you haven't heard it yet. In the grade 12 university physics, if Mr. Petrus does it, you will derive an equation for these energy levels, and you will find that as you go to higher energy levels, in terms of energy value, they actually get closer and closer together in terms of energy value. So the jump between the first energy level and the second energy level is fairly big, but the jump between the second energy level and the third energy level is smaller than that first jump. And then the third jump is even smaller, and the fourth jump is even smaller. It means that in terms of energy, the energy levels get closer and closer together. All right? In terms of radius, they don't, but don't worry about that. In terms of energy, they get closer and closer together, which means as I go from the first to the second to the third to the fourth, energetically, they actually get closer and closer together. This picture doesn't represent it very well. This picture represents it as being spread out, but in actual sense, this gets closer and closer and closer as I go from 1 to 2 to 3 to 4 to 5. That's one factor. The second factor, the subshells are actually spread out and have different energy values. 1s, right there. That's the only one in the first energy level. In the second energy level, we've got 2s and 2p. And it turns out that the p orbitals are of slightly higher energy than the s orbitals. So if we represent it in terms of a picture here, I've got 1s, and then in terms of energy, 2s is lower energy than 2p. So if I'm filling electrons and I'm starting from the lowest, I fill the 1s first, then I fill the 2s, then I fill the 2p. In the third energy level, we now have 3s, 3p, and up here in red, the 3d. And they're spread out as well. They're spread out so much that in the fourth energy level, in terms of energy, the 4s is actually below the 3d, which means if we're going to follow the Aufbau principle, after I'm done filling the 3p orbital, the next two electrons will go in the 4s orbital. And that's why it's not easy and straightforward, because we have this overlapping of the subshells. All right? So the order goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p. It looks almost chaotic. All right? But there is a way I can teach you so that you know this order without having to memorize a list, because memorizing just sucks. So I'm going to show you a way in which we can do this. You know what? Don't write this down. Don't write this down. This is a way in which many textbooks portray it, but I'm going to show you a way to learn this filling order by just using your periodic table and not having to worry about something like this. So the orbital filling chart can be used to place electrons in energy levels and sublevels of order increasing energy when drawing energy level diagrams. So in other words, we could use this to figure out which orbital to put them in first. But I'm going to show you another trick. So if you were to write out the energy levels for each, the subshells for each energy level, 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. You could actually put a 5g down here, but we never use it. 6s, 6p. We could keep going down with that, but we never use that one as well either. And then 7s, because we're actually full. Our periodic table is full at this point. If you draw it like this, all right, and you write them all out just in order, all those different subshells, you can get the order by doing this. This is kind of a silly thing. What you do is you start with a line that cuts at 45 degrees. Did I not orient the board? I didn't. I must orient the board because I got to get this straight. You start at a line at 45 degrees, and the first thing you come to is 1s. And I want you to write this down. No, I'll write it down here. 1, oh, get my pen going here. 1s. So we fill the 1s first. And you'll notice I'm out of numbers. So what I do is I backtrack through here, and I come back here at the same angle. 2s. And obviously I'm done there. So now I'm going to backtrack here, and I'm going to come at this angle right here. So 2p. Everything is looking exactly the way we would expect it to fill. 1s, 2s, 2p, and now I'm coming across here, and I'm at 3s. And that's great, but now I'm done, so I'm going to come back down to this row again, come at it at 45 degrees, and that's 3p. And now you might think 3d should be next, but as I follow this particular trend, you'll notice it runs into 4s, and that's where we have our first overlap. 4s. 4s. Next, I'm out of things, so I'm going to come back down to here, and it says 3d, 4p, 5s, and now I'm back down to here, 4d, 5p, 6s, down over to here, and now I'm way down here. Sorry for running into this thing here, but that's a 4f, etc., etc. And as far as I'm concerned, that doesn't really help anybody out, because really it's just kind of chaos. So what I want to do is I want to show you how we can figure out this filling order using our periodic table. Blank periodic table. 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4. 1, 2, 3, 4. 5. 1, 2, 3, 4. Perfect. Okay. And you know what you can do? Write down on the top of this orbital filling chart, on the top of that blank periodic table. Oh, excellent. Why did that reset? That's fun, in a non-fun way. My content, we want to do energy level diagrams, pictures, and do I have a blank periodic table on here? Whoa. Oh yeah, right there, blank periodic table. Put it right there. Beauty. All right. I just want to put this on the movie. I usually do this with you guys. Now, let's take a look at our periodic table. Notice that there are only 2, all right, atoms in our first row of the periodic table. That is not coincidental to the fact that we've only got, in the first energy level, 1 orbital, the 1s orbital, all right? So in this particular row, and don't mind that extra box. Does your table have the extra box? Don't mind that. Actually, the extra box might be better to be put right there, okay? Because this energy level 1, all right, right there is energy level 1. And these 2 boxes here represent the 1s orbital. This is exactly like our orbitron picture, all right? Actually, the orbitron picture is exactly what we kind of need. Actually, I'm going to grab it here for a second. So our periodic table actually shows us the filling order. There's the 1s. So this is being put into the 1s. 1s, all right? Now, once that's full, and we're not going to worry about these 2 guys because we took the 1 and moved it over there. Now we're into the second energy level. And for lithium and beryllium, these 2 electrons go into this 2s orbital. 2s. Now, notice how our periodic table is broken into these blocks that are 2 wide, 6 wide, 10 wide, and 14 wide. And that's because of the orbitals we're filling. As we move our way across the periodic table, you'll notice there's 1, 2, 3, 4, 5, 6, and the p subshell can hold 6 electrons. Because this is in the second row and it's got 6, these are my 2p orbitals being filled. As I move back to here, I'm now in the third energy level. This is the 3s orbital being filled. By the way, this particular whole group here is called the S block. Because all of the atoms in this part of the periodic table have their electrons going into the s orbitals. As I work my way across, I've lost my little marker here that I was writing with, black. 3s, 3p. You might think that we should fill the 3d next, but if we follow the periodic table, I'm in the fourth row, and I'm back into the S block. So without having to worry about that funny filling order thing, I can just look at the periodic table and say, all right, after I'm filling the 3p, I've got to fill the 4s. By the way, this entire area over here, what do you think we call this area? The p block. Because those atoms are going to have their electrons going into p orbitals. Here's where we've got to start thinking, though. After the 4s, we cut across this space that is 10 spaces wide. Remember the d orbitals, there's 5 of those d orbitals, and each of them can hold 2 electrons. That's 10. Even according to our little orbitron picture here, here's our d orbitals, but the difference is, even though it's in the 4th row, it's not 4d, it's the 3d orbitals. So in here, we've got 3d. If you can remember that the principal quantum number for the d orbitals lags behind the period number by 1, you'll have the orbital filling order. So if that's a 4s, when you get to the d, it's a 3d, because it lags behind by 1 in that period number. That's a lot easier than that funny cutting across business. So now if you use the periodic table, you've got 1s, 2s, 2p, 3s, 3p, 4s. I'm in the d block, 3d is being filled next. I'm back to the p block, and it doesn't lag behind the period number. So what's filled after the 3d orbitals are full? What is this going to be described as? Jenna? 4p. 4p is filled next. I come back to a new row. I'm in period 5. What's this guy? 5s. What's this next group? 4d, because it lags behind by 1. 4d. Now, on my real periodic table, what am I in? I'm in row 5, right? I'm now cutting across to here. I'm now at cadmium. Here we are. What's this guy going to be? Just shout it out. 5p, all right? Coming back around, what's this one going to be? 6s, row 6. Now, in our actual periodic table, when I get to this position, and it doesn't show very well on that table, but when I get to this position, I'm jumping down to the lanthanides, which means from 4s, I'm actually heading down to there. Sorry, from 6s. Now, I don't know whether you recall from that little funny chart that went across, but after the 6s, we actually fill with a 4f. And that thing will be 14 across there, because there are 7 f orbitals with 2 electrons in each. Now, the d orbitals, that principal quantum number, lags behind the rho by 1. But in the f orbital, the principal quantum number lags behind its rho by 2. So the f numbers lag behind its rho by 2. The d numbers lag behind its rho by 1. And the s and p numbers, their principal numbers, are the same as the period row that they're in. After we are done filling the 4f, we head back up into that spot. And what am I filling here? What is this going to be using the rule for the D number rule thingy? It's not an official rule, but 5D is going to fill next. 5D. And then, what's next? (6p), and then down here, what's this? 7s, and I'm going to grab a different color here. After 7s, I'm going to dive down in there. And what comes after 7s? Yep, 5f, because it's going to lag by 2. And then we're going to head back to the top. Again, it's a little bit ugly, but I think we get the idea. I don't know if those arrows help or hurt. Maybe they hurt. Maybe they're confusing. What comes after the 5f? 6d, because it lags behind by 1. And then in the end, what is this guy? 7p. Okay, excellent. And yes, there's been lots of elements discovered up to this point. I think they might even have the row complete now at this point. So that's up to what we know for elements, up to the end of 7p. That's it. There hasn't been one made with an 8s. We don't need that new row quite yet, but we're getting close. The s block, because those are the orbitals that are being filled at the time for these elements. The p block, because these are the orbitals being filled at the time for these elements. Just to complete it, we obviously have a d block. And obviously down here we've got an f block. So forget about that funny filling order business with that arrows. The d block number will lag behind the row number, the period number, by 1. And the f block, its principal quantum number, will lag behind the row number by 2. And you will then have the filling order with the periodic table that you have right in front of you and not have to worry about this funny thing. Okay? So what have we done? We talked about the rules in order to fill them. Start with the bottom. Fill them up first. Fill the subshells half full before you start doubling them up. Right? And then, in the end, double them up. All right? We've now defined the filling order. Let's start building our atoms. Okay? In terms of what you've learned in the past for Bohr diagrams, what we told you with Bohr diagrams was put 2 dots in the first ring and then 8 dots in the second ring, and then 8 dots in the third ring, which took 2 seconds. I am now at the equivalent point of Bohr diagrams. I've now told you where and how and what to put the electrons in. So now we're getting ready to draw our diagrams. So if we're thinking in terms of what you've learned in the past, we're finally ready to build our atoms so that we can think about where the electrons go. Okay, so let's go back to the PowerPoint. We've now got the order. Yeah, that's great. This is just an animation of what I just showed you. That's beautiful. That's good stuff. Okay, get out of the way. Yeah, that's nice. Coming back around the corner. Yeah, that's good. Good animation. Now, let me show you some pictures representing our energy level diagrams. Here I say graphical representation, schematic representation. You could put schematic in there if that's on your mind from my description. This doesn't represent what the atoms actually look like. It just represents a very useful way of representing the atoms and places to put the electrons. The orbital diagrams that I'm going to introduce you to are essentially these guys. And they're a more true representation to the way we think an atom would look if you could see it. But that's a pain to draw all the time, all these funny shapes. So essentially we need some places to put some electrons, and we want to just represent them as simple shapes. Now we're not even worried about the nucleus, we're not worried about protons, we're not worried about anything like that. We're just worried about where to put the electrons. I'm going to draw these pictures. I start from the bottom at the lowest energy level, and then I work my way up. A simple circle is used to represent the s orbital, and I write it with the letter S underneath. This circle was probably chosen because the s orbitals are spherical, but this circle does really not represent a spherical orbital. This circle simply represents a place to put electrons. When we draw electrons in an energy level diagram, it looks like this. Arrow up with half an arrowhead represents an electron with spin up plus 1/2. An arrow down represents the second electron. So it's not that we're actually putting dots on a ring, we're just putting these electron markers in this shape to represent the fact that we've put some electrons in the first orbital. Notice I don't label this as 1s or 2s or 3s. We use the same representative for whichever s orbital we're dealing with. This is just a general representation. I'm not drawing actual atoms yet. P orbitals. Now you know what? Some textbooks just represent them all as circles. For the p orbitals, they'll put 3 circles fairly close together. My chemistry teacher did this in terms of these shapes. I like them because I can distinguish them just by looking at them. And my teacher represented these p orbitals, and I'm just going to put here the p orbitals. And just as some sub-information, if you've got a pencil and really light, this kind of represents, and you don't have to write this one in every time we draw this, but this box represents the px orbital, this one could represent the py orbital, this could represent the pz orbital. So these boxes represent each of the dumbbells, but I'm not concerned about the dumbbells. I just want a place to put the electrons so I can understand where the electrons are going. I don't want to be burdened by this complex picture of what the atom is looking like. I just want to put electrons into them. And 2 electrons will go in each of those when they're full. I'm not going to draw the electrons in right now. You know the way the electrons look. I'm just representing the shapes at this point. D orbitals. D orbitals I have chosen to represent my 5 triangles. 1, 2, 3, 4, 5. D orbitals. Each of those little shapes represents one of our clover leaves where we can put 2 electrons. And I'm not going to put them in right now. And we very rarely draw f orbitals. I actually am not going to draw any f orbitals. in this course because we don't get into bonding with things that have f orbitals. I've seen it represented as ovals and various other things, but I use ovals for a different thing that's a little later on, so I'm not even going to worry about the f orbitals right now. But there would be 7 of them, and you could use whichever shape you'd like. We could use hearts. Hearts, right? Ladies, the dot of the eye with a little heart on it. No? You all went through that phase? Guys, Ben, did you ever use the heart? No, okay. Anyway, you can use whatever you want. You just need 7 of them, all right? So let's not worry about it. Okay, so these are our energy level diagrams. Let's get ready and start drawing some of these things. Now, don't worry about this. This puts together our little simple shapes along with the filling order, right? So here they're representing it not with shapes, but just with little lines that you could put the electrons above and below. There's your electrons there. So 1s has 2 electrons in it, 2s, then 2p, then 3s, then 3p. But notice the 4s representation is slightly of less energy than the 3d. So we would fill the 4s next, then we would fill the 3d. Then the 4p, then the 5s, then the 4d, then the 5p, then the 4f, etc., etc., etc. Actually, there's an s in there. This is just putting together our orbital filling order along with our little pictures. Don't worry about it. Okay. Let's draw some atoms. Now my next slide actually defines electron configuration, but you know what? We're just gonna look at it. We're gonna read it over, and then I'm gonna get to the examples because I really wanna give you an opportunity to start drawing and start thinking about all of these rules. And it seems to be dragging on a little bit, which is fine. We're in a good spot here. But I'm also then going to introduce you to this shorthand way in which we can do things called the electron configuration, and we'll take care of both things in one shot. The electron configuration comes from an energy level diagram, but we don't really need that in order to find electron configuration. We can do it in other ways. So I'm going to show you how we can solve these pictures and how we can draw them up. So in order to draw an energy level diagram, we need to determine the number of electrons that needs to be placed. That's easy. That's just like back in grade 10 where we look at the atomic number and we know that we need the same number of electrons for a neutral atom. So we just need to determine, how many electrons we need to place in there. First, put the electrons in the lowest available energy level. So start at the bottom. Fill your electron bowl from the bottom to the top. And then when you get to subshells, half fill them before you pair them up. You follow those rules and you will get the energy level and electron configuration correct, except for a handful of exceptions, which I'll teach you a little later on. There are some exceptions to these rules. So let's take a look at some examples here. Again, don't write this down, but I'll talk about the electron configuration. It's this shorthand notation, so we don't have to draw all these pictures. And the full electron configuration is where we start at the 1s. I'll talk about that a little bit more later on. So just put EG, and I'm actually going to switch over to the Smart Notebook, and we're going to start with hydrogen and helium. Oh, no, I clicked on that. It's going to open another one. That was just a mistake, is what that was. That's not what I wanted to do. I already have one open here, you see. And I can just go to here. And let's bring this up. Okay. All right. So the first example I want to do is hydrogen. All right. So we're going to deal with example hydrogen. Okay. And for hydrogen, I'm going to do the energy level diagram. And I'm going to bring it all the way up here. Let's write this thing out. This saves me from having to actually write it down. We're going to do the energy level diagram. All right. It's kind of handy. Huh? See that trick? So you got to write energy level diagram. That's no fair, is it? And we're also going to do the electron configuration. And look at my screen is not big enough for that. Silly thing. Let's try auto hide. Get rid of it. Why are the words so big? Did that cause someone great distress? All right, the energy level diagram. Hydrogen. Hydrogen has one electron. What's the first orbital that we're going to fill? This is hopefully a really easy answer. What's the first orbital that we fill? What's that? 1s. Sure, laugh at okay, 1s. Notice how now I put 1s there instead of just s. And how many electrons do I have to put in a hydrogen atom? 1. So this isn't very exciting because all I have to do is put 1, and I've started at the bottom. That's the energy level diagram for hydrogen. That's essentially like a Bohr diagram with 1 ring and 1 dot, except here it tells us that we've got 1 electron in the 1s orbital. It's the same thing. The electron configuration is really easy. Instead of drawing all this, we write it like this, 1s superscript 1, to represent the fact that there's 1 electron in the 1s orbital. All right? So if I keep going, let's do another example down here. So you can keep your energy level diagram and your electron configuration going, and we will do next HE. HE. And which orbital will I be using for HE? Yep, just the 1s. How many electrons go in that? 2. I half fill. I'm done. So I've got to go back. It's full. That's the energy level diagram for helium. Notice its orbital is full. It's a noble gas. The electron configuration 1s2. All right. Let's do a beryllium. Beryllium, Be. Which orbitals am I using? A 1s and a 2s. I'm going to put the 1s below the 2s. Notice I don't care about the nucleus. I'm not worried about the number of protons. That's all built into the beryllium. How many electrons go into a beryllium atom? 4. First, I've got to fill the 1s. There's 2 of them. I fill the bottom first. Then the 2s. Half fill. I've got 1 more electron left. There it is, right there. The electron configuration, 1s2. I've got 2 electrons in the 1s. And 2s2. And I think they separate them by commas. I think they do. Yeah. Yes, they do. Let's do another one. Oh, I'm trying to extend the page here. Not working very well. Extend the page. Extend the page. Let's do carbon. carbon. Then what am I doing? I'm writing in blue all of a sudden. Start by drawing up your orbitals. I'm going to be using a 1s and then a 2s. And what comes after the 2s? Sorry? 2p. I always draw it off to the side. 2p. All right, I've got my orbitals. And I got my orbitals by using the periodic table and the p blocks and the s blocks. How many electrons have I got to put into this thing? 6 electrons, because it's got an atomic number of 6. So 1, 2, that's full. I've filled that sublevel. 3, 4, I filled that sublevel. 5, now, you might think I should pair it up, but according to Hund's rule, I got to half fill them all, 6. So here, carbon has 2 unpaired electrons. Its electron configuration, 1s2, 2s2, and this is why I don't like the electron configuration so much. This is still written as 2p2, but we have to use in our mind the fact that we know that they'll be by themselves. We've got to almost visualize that. Let's do oxygen. Oh, I'm hoping you get the idea of this. We're using repetitive stuff. Hopefully you're drawing ahead of me. 1s, 2s, 2p. I'm getting a little sloppy, but that's okay. You probably are too. How many electrons in oxygen? 8. 1, 2, 3, 4, 5, 6, 7. I've half filled. Now I've got one more. These aren't full, so I can't go on to the next orbital. So I start pairing them up. 8. Oxygen has 2 unpaired electrons. We knew that. Oxygen needs 2. Oxygen needs 2. In terms of the electron configuration, 1s2, 2s2, 2p, 1, 2, 3, 4, 2p4. All right? And one last example, and then I'm going to talk about how we can shorten this up, because if I give you one of these way down here, as you can imagine, you're going to be drawing forever. So we want to come up with a shortcut way so that we don't have to draw forever. But one last example here, and let's do this as, well, we'll do it as neon, N-E. And you can go ahead and probably draw this without my assistance. 1s, 2s, 2p. How many electrons in neon? 10, I believe, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Its p orbital is full. It is stable. It's a noble gas. In terms of the electron configuration, 1s2, 2s2, 2p6. All right? Okay? And I just want to show you one other thing. If I were to be doing this as an orbital diagram, what it actually looks like, it would look like this. And this is why we don't do this very often. So I've got some pictures of some orbitals here that I've created. I'm going to be using these later on. And these circles do represent our spherical orbitals. You'll notice here I've got some p orbitals that look like the dumbbells. Here I've got the py and the pz, and here I've put all 3 of them together. So if I wanted to do neon, I would need a 1s. So there's my 1s. And I would need a 2s, which is bigger than it. So there's my 2s, with the center being where the nucleus is. And then I would need those 3 p orbitals. I could put them on individually as x, y, z, but for the sake of ease, I've built this little guy here to be all 3 of them. And so there they are right there. Let me just get it straight on the center. And that would be what we feel neon looks like. All right? And you can notice that that's kind of a pain. If we were to draw the electrons in, I would have 2 of them in here, 2 of them in the next circle, 2 of them in each of the dumbbell pairs to make 10 of those electrons. So that's an orbital view. Okay? All right? Couple of things before I show you one more example or a little shortcut here. We call this here, we call this the full electron configuration. All right? Same with this. We call this also the full energy level diagram, ELD. Full electron configuration and full energy level diagrams start right from the 1s orbital. But I'm going to show you a shortcut now to do larger elements. Okay? So full, they start from the 1s orbital. They start from 1s, right from the beginning. Let me define something here first, and then we'll finish off. You can write that next, and then I got a handful of more examples, and then just a very little bit of work. There's not much homework on this stuff. In chemistry, the valence electrons, the outer electrons, are really the only important ones. The outer electrons are the ones that undergo sharing and trading. So we don't need to draw every level over and over again. So we do what we would call a core energy level diagram or a core electron configuration. And this allows us to deal with and draw some of the larger ones. Due to the fact that that previous noble gas configuration will always be the same for elements that are larger than it, we don't need to draw that chunk. We can just represent it in brackets. For those of you who are waiting, this time you can put examples. And instead of just energy level diagram, put core energy level diagram and core electron configuration. And I'm going to do a few examples here. And then the homework. So just like our examples above, we're going to be now drawing core energy level diagrams and core electron configuration. So again, I'm going to switch back to the Smart Notebook because that's a convenient way to kind of deal with that. So I'm just going to extend the page. I do have little titles for it, but I'm going to just do it here. In this case, it's going to be core energy level diagrams, ELD. I'm going to use that a fair bit. And again, core electron configuration, I'll just call that EC. And let's now do something like, let's do our carbon again, all right? Just to kind of illustrate that we can do this with anything. So the way this works is we go to the previous noble gas and we simply say, all right, that's going to be the core of this particular thing and we don't care about it. So instead of drawing 1s, we write off to the side of it an HE in brackets to the left. And then I just continue from that. So again, I've got still my 2s and my 2p, and now I need to draw that. So the HE takes care of the 1s. I still have my 2s and my 2p. So now I'm just worried about that last row of electrons. Because I'm not really totaling from 6 anymore, the way I work my way through is, look at this. My S block is full, so I'll put my 2 electrons in the S. 1, 2. And I'm 2 electrons into the P block, so I need 2 more electrons to go into that P. 1, 2. Not a lot of savings when you're dealing with something like carbon because you've only got the 1s orbital that you kind of saved on, but still, it saves a little bit of writing. In terms of the core electron configuration, the same thing. HE, and then 2s2 and 2p2. It means we get rid of what's on the inside there. So let's now jump down to something like scandium, which we would have lots of drawing to do if we were doing it the long way. So SC. My next example is SC. SC. So the way this works is we go to the previous noble gas. I get to the end of 4. I work my way up. Argon. Argon is the core of this thing. I don't need to draw all those electrons that represent argon. I can represent it simply by an AR. Now I work my way back to scandium. What's the next orbital going to be? Ben? 4s. 4s. And it's going to have 2. And what's the next orbital after that? Yep, 3d. I'm going to put this way over to the side. 1, 2, 3, 4, 5, 3d. The reason I put it over to the side is because if we had enough electrons, we would eventually fill that 4p. Now, you don't have to put that in. I'm just giving you kind of a perspective to where it would sit. But this gets filled first. How many electrons in am I? Just 1? We're 1 electron into scandium, 1 electron right there. And I moved into that space for the electron configuration. Hopefully you can figure it out. For the electron configuration, the same thing. Argon, 4s2, 3d1. Okay? And I'm looking at time. Let's take a look at what I want to do next. Let's do an arsenic. Arsenic. I'm taking some of my examples away because I'm just noticing the time is there, but we're not bad. We're okay. So let's do arsenic. AS. What am I? AS. You got an answer already, or a question? Yep. Yep. Are you looking on your periodic table? Have you been cheating ahead? Nice job. That's good. That's being very observant. That's excellent. I don't know if you've taken a close look at your periodic table, but all of these electron configurations are already on your periodic table. They're right there. They're right in front of you. There's no need to actually look and learn the periodic table and how to draw it because they're all there. They're hidden at the bottom of the box. But I'm going to give you a quiz in, a few days, and I'm not going to let you use that periodic table, so you're going to have to figure it out from the actual location. I don't care which order you put it in. The official order, they like to put the lowest numbers first. And there's a good reason for it. But I'm not that picky on whether the lowest number goes first or not. But the true official way to do it is put the lowest numbers first. And you'll learn why they do that tomorrow. But I'm not concerned about it here. So if you took a look at SC, scandium, did anybody find it? Did you find it on your periodic table? You find the electron configuration? Have you found them on the bottom? Take a look. It'll have argon, 4s2, 3d1, except the 3d1 will be first. Did you find it? Anybody knows that? All right. I'll talk about why that is. So you know what? Let's cheat. Let's cheat on this. Thanks, Ben. We're going to cheat. Arsenic. What's the electron configuration? Yeah, read it to me. Jeez. It's no fun. Yeah, what do you got? Argon. 3d10. 4s2. 4p3. Now I'm hoping we could have got that just from a regular table, right? Arsenic, argon is the previous one. I would have put 4s2 first, then 3d10, right? And then 4p3. I would have had it flipped like that. Again, its position can easily be identified. Arsenic, 4s2, 3d10, we've used them up, 4p3. Okay? In terms of the energy level diagram, AR, all right? 4s, 1, 2, 1, 2, 3, 4, 5, 3d, they've got 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm 3 electrons into the 4p. 4p, 1, 2, 3. Okay? All right? I wanted to do one way down here in the F block, but the time isn't going to let me. You will have examples that will be working down into that F block. All right? But just be aware, maybe just try one. Maybe as an example, I was going to have you do a PM here, promethium, right? You can see there. Maybe give that a shot. We'll take that up tomorrow as like an add-on there. Try promethium. It means you've got to get into the 4Fs. That's what I wanted you to do there. What's that? Oh, you can pick whichever shape you'd like. Little hearts. That would be entertaining. Just a handful of problems on drawing energy level diagrams and electron configuration.